Hi guys, so today we're going to start our actual calculus material. And the first thing we're going to look at is limits. Now while the terminology here and some of the things you see written may be a little bit new to you, this idea you've actually already seen before in this class. So the first thing we're going to talk about is this function that's given. That is the parent function for rational functions, and it's the function 1 over x. And when we first looked at this function, we talked about what was happening as x approaches a certain number. So for example, we said as x approaches, let's say as x approaches infinity. Okay, so as my x's get bigger and bigger and bigger forever, we could see what our y's are doing. As those x's kept getting bigger and bigger and bigger and bigger, those y's were approaching that horizontal asymptote that had a value of 0. Same thing as x approached negative infinity, the y's kept approaching 0. So we've talked about that, we've seen that before. What we're going to do now is we're just going to write that in a different form in order to talk about a limit. So as a limit, you would see that written as the limit as x approaches infinity of 1 over x is equal to 0. So that's saying as my x's are approaching infinity, then my y's are approaching 0. That's what it's equal to. So your basic notation for a limit would be the limit as x approaches c of f of x, so whatever function is you're looking at, is equal to L. So the limit is, that's your final value. And again, the limit is what your y's are getting closer to. As my x's do something, what are my y's getting closer to? Now in this case, my x's, as they kept getting bigger, they were going to approach 0. They wouldn't necessarily, in this case, actually touch 0, but that doesn't mean that it can't. Another example here is if you look at the limit as x approaches 1 of 1 over x. So from looking at your graph, you guys can see as I'm getting closer and closer and closer to the x value of 1, my y's keep approaching that point, which is 1, 1. So we know that that's going to end up being 1. Now I'm going to show you that a little bit more detail on the calculator. So in order to see what our limit is, we look at the left side of that x value, we look at the right side of that x value. So what we're going to do here is we're going to look at, here's my graph, this is 1 over x. So what I'm going to do is I'm going to see as my x's get closer and closer to 1 from the left side. So I think of numbers that are to the left of 1, something like 0.9. Okay, that's pretty close. And I have a y value of 1.11. Well, let's look at something that's closer, a little bit more moved in that way. Maybe I could say as x is equal to 0.99. That's getting closer to an x value of 1. My y's are getting closer to a y value of 1. Okay, then I could do 0.999. And again, much closer to 1. Not quite there, but getting closer. So as those x's keep getting closer to 1, so as I keep moving further and further closer to that value there, okay, you guys can see what your y's are approaching. Now the other thing we need to make sure of, though, is that the right side is doing the same thing. And we're going to talk more about that in a second in case that doesn't happen, but let's just make sure our right side is also approaching that. So I'm going to pick a number to the right of 1, like 1.1. Okay, and I get 0.9. Then I'll pick another value that's closer on the right side. That would be something like 1.01. And I get 0.99. So let's move a little bit closer. 1.001. 0.999. And again, as I get closer from the right side, my y's are approaching 1 as well. Okay, so that's just what it looks like in terms of a table. All right, now this you do not need to write down, but this is your actual definition of a limit. All right, this is what we just talked about. And again, the important things just to notice here, that notation that we just talked about. Okay, as x approaches c, c is just whatever value it is we're talking about. We're looking at as my x's do something, what are my y's coming close to? And then the other important thing here is from either side. Okay, so we do have to look at both sides. All right, so again, there's multiple ways you can solve for a limit. You can look at a graph, you can look at a table, but sometimes it's just really easy to solve these algebraically. So for example, if I look at this function, I want to find the limit as x approaches 1 of the function x squared plus 3. Now what's nice about some of these functions, I know the function x squared plus 3, that is just a continuous parabola. It doesn't do anything crazy like jump around or have holes in it or have restrictions. It's just a straight continuous function. So the easiest way to find that limit, I can just take that x value and plug it in for x. So if I plug in 1, I get 1 squared plus 3, which is 4. So the limit as x approaches 1 is 4. If you were to look at a graph, you could prove that this is true, but sometimes it's really easy just to plug in those values. Now the problem with just plugging in those values is it won't always work for us. So if you look at this next one, for example, this is a rational function. So if I plug in -1, I'm going to get 0 at the top of this function. Then if I plug in -1 to the bottom, I also get 0. Now this is really important. If you get 0 divided by 0, you cannot draw your, you cannot figure out what your answer is without doing a little bit more work. Okay? This is called our indeterminate form of the limit. And indeterminate is not an answer. Okay? You cannot just say, oh, it's indeterminate, I'm done. What this really means is you need to do more work, you need to rearrange the equation, you need to do something algebraically to actually find out what your answer is going to be. So indeterminate is not an answer, it means do more work, okay? Now if you look at this equation, one of the things we're used to doing with rational functions is factoring, okay? We always factored first. So if I go ahead and factor this, I know the bottom is going to factor into x plus 1 times x minus 2. Then what happens is those x plus 1's cancel out, and I'm left with 1 over x minus 2. Now if I take -1 and plug it in, I'm going to get my answer. And I get 1 over -3, so it's a -1/3. And that is my answer. That is my limit. Now, will this graph actually touch the point -1, -1/3? Okay, no, it's going to be an open circle, it's going to be a hole there. But as my x's get closer to -1, my y values are getting closer to -1/3. And again, you can check that in the calculator if you want to. Let me go ahead and plug that in. So I have x plus 1 at the top. And that is divided by x squared minus x minus 2 all right, and you can't really see that hole there. We know it's there because we factored. So what we're going to do is we're going to pick, again, we're going to pick x values that are close to -1 from the left side and the right side. So let's say I look at a value like -0.9. Okay, and then let's say I do -0.99. All right, I'm getting closer and closer. And you can see those y values are getting closer and closer to -0.33333, which we know is a -1/3. If I look at the other side, this would be the left side, I could do -1.1. And then I could try -1.01. Okay, so -0.33, getting closer. Whoops, I forgot the 1. 1.001. Okay, closer and closer and closer to -0.333. But if I just plugged in -1, I don't get that value because we know there's a hole there. Okay, so your graph does not actually have to touch that point. We're just seeing as my x's get closer and closer to it, what are my y's getting closer to? All right, now we're going to look at a couple more graphically. This is a piecewise function. And when you look at this picture, it's really important to understand what the question's asking here, okay? This first one on here, it wants to know the limit as x approaches -2. Okay, so what I do is I find -2 on my graph. So -2 is right there, that point. Now in this case, I look to the left of -2 and I see what y value I'm coming close to. Then I follow the graph on the right of -2 and keep moving closer to it. And I see what y value it's approaching. In this case, it actually touches that point, and the y value that it's getting closer to is 0. Now this is where it gets a little bit tricky. This is probably the most missed thing I see when people are looking at limits on a graph. We want to look at the limit as x approaches -3. So what we do is we find our graph where -3 is. Okay, so -3 on my graph, there's this part right here. There's also this open circle up here. Okay, now this open circle up there, nothing actually approaches that dot. Since nothing is actually approaching it, we are not going to use that to figure out part of our limit. Okay, so we're going to look at the graph to the right of -3. This is the graph that's to the right of -3. So what we're going to do is we're going to look at those x values. As those x's are getting closer and closer to -3, the y values are approaching that open circle. Then I look to the left side of -3. And as those x's get closer and closer to that x value, those y's are again approaching that open circle. Since your y values are approaching that open circle, your limit here is -1. Okay, it does not have to touch that point, it's just what it approaches. Now if I was actually to evaluate this function at that point, like let's say I did f of -3, that's when I would use that filled in circle and I would get a positive 1 as an answer. Okay, but that's the only time you use that closed in circle. A limit is not what your graph is equal to at that point, it's what your graph is approaching from both sides. All right, then the last one we're going to look at is at -1. So as my x's approach -1, now if you look on the right side of my graph, that's up here. So on the right side, I'm approaching this closed circle there at 2. Okay, so the right side is approaching 2. Now I find the left side. If I look to the left of -1, I'm approaching this open circle, which has a y value of 1. Since the left side and right side are approaching two different values, then what we say is that this limit does not exist. And that's when you get to quote Mean Girls. Now this is probably the most common case you guys are going to see in this class when we look at limits for graphs where they don't exist. There's actually 3 cases where a limit does not exist. Okay, the first one is one we just looked at. If the left side and the right side are approaching two different values. Okay, if the left side and right side are approaching two different values, then the limit does not exist. Another case where the limit does not exist is if your graph is unbounded. Okay, if the graph is unbounded, that means if it keeps on just going on for forever, that limit doesn't exist. So for example, if I did the limit as x approaches 0 on the function 1 over x, that would not exist because at 0, that graph is going up towards infinity or down towards -infinity. So it actually doesn't exist for 2 reasons. It's unbounded and it's also doing different things on the left side and right side. Now we can describe that behavior. We can say it's going towards infinity or it's going towards -infinity, but that limit itself doesn't really exist because we can't actually find it. And then the last one, this one's really kind of rare. If your graph is oscillating a crazy amount, okay, if your graph is oscillating, and that looks like an A, not a C and an I. And I forgot the S. I'm having trouble spelling today. My goodness. Sorry, guys. Okay, this one you won't see as much. An example like this, I'll show you in the calculator. I would do the limit as x approaches 0 of the sine of 1 over x. Okay, it's a function we haven't really seen. That's why I'm going to show you it on the calculator. So I'm going to graph the sine of 1 over x. And again, I'm looking specifically when x is approaching 0. I can find this limit actually in a lot of different x values. The one place I can't find it though is 0. So I'm going to zoom in a little bit here so you guys can see what this is doing. Let me zoom in a little bit more. Okay, so you see how that graph is going crazily up and down the closer and closer you get to 0? So as I plug in values that are close to it, like let's say I try 0.01. then negative 0.5. Then I do 0.001. Now it's positive. And then if I do a 0.001, okay, so it's really kind of hard to see what that graph is actually doing as you get closer and closer to 0. Because it just keeps bouncing back and forth between positives and negatives and all over the place. Okay, so that's a case where we would, the limit would not exist.